We just finished our unit on gases, and we are starting chapter 11, which is property solutions, but it turns out that you can have gas solutions. Okay, so air, for example, is a solution of all types of gases, right? Nitrogen, oxygen, carbon dioxide, and a bunch of other gases. And you may remember from our gas unit that all gases form solutions with all other gases. They're completely compatible. They are not selective like liquids and solids are. And that's primarily because gas particles are far enough away that they don't feel significant intermolecular forces between other gas molecules. So they mix very well with any other gas because of that. A quick reminder for the definition of a solution: it's simply a homogeneous mixture as opposed to a heterogeneous mixture. And so that's when you mix things together and it looks like one homogeneous composition. The solvent is, you usually think of it as the component that's doing the dissolving, but that's not always clear. For example, in the solution that is air, what is the solvent? So then we need to go back to the root definition of solvent, which is the component in the solution that's present in the largest quantity. The solute is anything else that's not the solvent. Okay, so for air, the solvent is nitrogen gas because it's there in the largest quantity, and the rest of them are solutes. You may remember learning about intermolecular forces in the first semester of chemistry, and that would be London dispersion, dipole-dipole, and hydrogen bonding. We're going to talk a bit about them in this chapter also, because they play an important role in whether or not two components will form a solution or not. Quick vocabulary. Miscible refers to two or more liquids. Okay, so it's specifically talking about liquid mixtures that are completely soluble in one another. So rubbing alcohol. It's a mixture of isopropyl alcohol and water. Those two liquids are completely miscible with one another. It looks like one homogeneous composition. Drinking alcohol is the same way. Oil and water would be a heterogeneous mixture, right? Because you'd have two distinct different layers. Whether or not two components, whether they be liquids, solids, or gases, whether or not, well, not gases, we'll get those out of there because they mix with all other gases, liquids and solids, whether or not they make a homogeneous mixture depends on how the different components interact with each other. Right? So for example, how compatible is isopropanol with water? Because the two are going to have to interact in a mixture if they're going to make a homogeneous mixture. Here's a very common example of components that do not form a homogeneous mixture. So if you have any type of hydrocarbon, something containing only carbon and hydrogen atoms, for gasoline, wax, octane, it's just hydrocarbons. They are nonpolar. And just a note here, I may be pulling on memory strings from last semester chemistry, so if you find you need to review any of these topics, there are recordings on all of them on my YouTube channel, okay? So if you need to review polarity and how you determine if something is polar or nonpolar, you need to go back and do so then. So any type of hydrocarbon is nonpolar, okay? And that's because the carbon-hydrogen bond is nonpolar. Their electronegativities are so close together that they are classified as a nonpolar bond. And of course, if all you have is nonpolar bonds and no lone pairs of electrons, you have a nonpolar molecule. Water, on the other hand, is a polar molecule. It has polar bonds. Oxygen and hydrogen have significantly different electronegativities. All right, and it's also not symmetric, so that allows it to be polar. So the old saying is that like dissolves like. polar substances will tend to dissolve other polar substances, and nonpolar will dissolve with other nonpolar substances. Like dissolves like. So gasoline, octane, any of those hydrocarbons will not be soluble in water because of the difference. You should be able to make a very good prediction on whether or not components are going to be miscible or soluble in water. Let's look at a few of them here. And this is something you should practice. There are some worksheets uploaded, so it's important to practice that. The first thing two things you need to be able to do to predict. Number one, you need to be able to draw Lewis structures, and you may have to go back and review how to do that. Because in order to be polar, you need to have polar bonds, so you need to remember how to identify polar bonds, difference in electronegativities, and in order to be a polar molecule, in addition to polar bonds, you also need the molecule should be asymmetric. It can't be perfectly symmetric, or it will cancel out any of the polar bonds it has. So you draw the Lewis structure to say whether it's polar or nonpolar, and then it's a good idea to look over the intermolecular forces that can exist between the molecule itself and between that molecule and what you're trying to dissolve it in. So let's look at these one at a time. Alrighty. Carbon tetrachloride. I'm going to do a quick kind of reminder of Lewis dot structures to help you out here. Count total valence electrons. Carbon has 4. Each of the 4 chlorine have 7. So there are 32 valence electrons. So the rules for Lewis dot say that you draw single bonds to begin with between your central atom, which is usually the atom that is shown first in the equation. And then you give the outer atoms an octet, assuming you don't run out of valence electrons to place. So I'm going to give all 4 of the outer chlorine an octet. And now count and check how many electrons you've used totally. I have now used exactly 32 electrons. So I'm done, but that's good. They all have an octet. They're all great. So now, is this polar or nonpolar? Well, it has to meet the 2 requirements. Does it have a polar bond? Yes, carbon-chlorine bonds are polar. Actually, it turns out most bonds are polar. You can look at a table of electronegativities, and as long as the difference in electronegativity between 2 atoms is greater than 0.4, it's a polar bond, but most of them are. Anyway, so it's a polar bond. Now we need to know whether it's symmetric. So now we're going back to shapes, which is last semester also. If you have 4 domains off a central atom, it is a tetrahedral shape. And in a tetrahedral shape, when all of the 4 atoms that are bonded to the central one are the same thing, it's symmetric. And so what happens in that case is even though the bonds are polar, the dipole moments from each of those bonds cancel each other out. Okay, they're all pulling with equal strength in opposing directions, and so there's no net movement for the central atom. So that is non-polar. Let me erase and go to the next one. Would you expect a non-polar molecule to dissolve in water? No. Right? Water is polar, like dissolves like. So that I don't expect to dissolve. Let's figure it out for ammonia. 5 valence for nitrogen, it's in group 5A. Each of the 3 hydrogen have 1 valence. So we have 8 valence electrons. Nitrogen's a central atom. Start out by drawing single bonds to each of the other atoms. Now I've used 6 valence electrons. I have 2 more electrons to place. Hydrogen cannot hold any more electrons. It can only hold a maximum of 2, which it already has with these bonds. So the 2 extra electrons are a lone pair in nitrogen. Now, polar bonds. Is the nitrogen-hydrogen bond polar? You can prove it yourself from an electronegativity chart, but yes, they are polar bonds. In addition to that, this is not a symmetric molecule. It has 4 domains again, so it has a tetrahedral electron domain shape. But the molecular shape, whoops, that should be a straight line. Yeah. The molecular shape is trigonal pyramidal. Not sure if you remember that. But you can tell by looking at it, it is not symmetric, okay? There is a net dipole going up towards the nitrogen in its lone pair. So this is polar. You expect a polar molecule to be soluble in water because they're both polar, like dissolves like. Not only because they're both polar, but guess this, look at this. What type of intermolecular forces does water have and ammonia? Water has hydrogen bonding, right? Ammonia is capable of hydrogen bonding too. So this is a match made in heaven. Those two are highly compatible, and ammonia is very soluble in water. And all of your cleaning products that have ammonia in them are actually ammonia water. So it's very common. If I were to draw hydrogen bonding between the two to show you what a nice interactions they have, let me change colors. It would look like this. So, see, nitrogen has nitrogen has 1 lone pair, oxygen has 2 lone pairs. So the partial positive hydrogen on one of them would associate with the electron-rich oxygen on the other. And then we could do the same thing with a lone pair on nitrogen. Show it associating with the partial positive of another water molecule. Okay, anyway, so they are very fond of one another and very soluble in one another. So real quickly, so I don't bore you silly here, let me do the last 2. Hydrogen fluoride. It's an easy one, right? It's a linear molecule, but this is a polar bond. So it is polar overall, right? It's not, can't be totally symmetric with linear in 2 different atoms. So that will, and as a matter of fact, that can hydrogen bond too, right? So it's going to be very compatible and very soluble in water. How about molecular nitrogen? That you should be able to look at just now is completely nonpolar, right? Totally symmetric. It turns out if you did draw the Lewis dot structure, it would look like this, but that wouldn't change your prediction of whether it's polar or nonpolar. That is nonpolar, and it would not be expected to be soluble in water. So if you want a neater typed out explanation of what I just went through kind of in a sloppy way on the last slide, here it is. Okay, continuing to talk about solubility of gases in water. Their behavior as trying to get them to be soluble in water is quite a bit different than other liquids and solids that are soluble in water. One of the key differences is that as you increase temperature, for most things that you dissolve, like think about trying to dissolve sugar or salt in water. If you had to do it very quickly, what would you do? You would increase temperature, right? So most things, as you increase temperature, the solubility goes up. Here's solubility in the y-axis, right? So there's a couple weirdos, but for the vast majority, the solubility goes up with increasing temperature. Look at gases. As we increase the temperature and we're trying to dissolve a gas in water, look what happens to the solubility. The solubility of gases go down with increasing temperature. What is going on? Okay, very easy, right? You think of carbonated soda. So I have a can of Coke, and it's all bubbly, right? Because it has dissolved carbon dioxide in it. if I pour that Coke into a pan and turn the heat on underneath it, what's going to happen? The carbon dioxide's going to escape, right? It's going to boil out, bubble out, right? So gases, not because of their compatibility, but simply because the heat's going to give them extra kinetic energy to escape back into the gas phase. So these are solubility curves. Be able to analyze them. Let me show you a little bit other information you can get out of them. Some of the common questions you can be asked. So a real easy question I might ask would be, let's see, what is the solubility of calcium chloride at 10 degrees Celsius? So you're like, okay, here's 10 degrees Celsius. Now I've got to find calcium chloride curve. Here we go. And its solubility, that's the maximum amount of solute that will dissolve. So take this up at 10 degrees. Oops, I went too far. The solubility of calcium chloride at 10 degrees is about, I would say, 62 grams of calcium chloride, look at the units there, per 100 grams of water. It's kind of weird units for solubility. Okay. Another easy question I could ask you might be, let's see, I might say, like, compare potassium chloride and sodium chloride. Which is more soluble at 10 degrees Celsius? Okay, here's 10. Here's potassium chloride, here's sodium chloride. So you'd say, okay, sodium chloride is. Which is more soluble at 60 degrees Celsius? Go to 60, go up to sodium chloride and potassium chloride. Now suddenly they've switched places and potassium chloride is more soluble. All right, so just get familiar and be able to, and this is just a closer look at the effect of increasing temperature on the solubility of gases. All right, still talking about dissolving gases in a liquid. We've talked about how temperature affects, so we know that as temperature goes up, solubility of a gas goes down, right? What about pressure? Pressure goes up, what happens to the solubility of a gas? So let's see, let's think about carbonated beverage again. When you take the top off, like a screw top, let's say for a Coke, what happens as soon as you take that top off? It fizzes, right? You can tell there's gas just waiting to get out. So what happens to the pressure when you open that cap? The pressure goes down, right? So what's happening, do you think, to the solubility of the carbon dioxide in the soda when you reduce the pressure, when you take off the cap? It goes down, right? So the opposite can happen. So if you increase pressure, so in this closed container, so let's imagine that that's water and that's carbon dioxide. As you start increasing the pressure, and we're going to do that by reducing the volume, right? Reducing the volume increases collisions and therefore pressure, right? When we have increased pressure, you essentially force more of the gas molecules into the solution phase. So increased pressure means increased solubility. And I'm kind of hoping that's intuitive for you. Carbonated beverages actually are made under pressure. So the manufacturing plants have devices that will create carbon dioxide under pressure, forces a lot of it in solution, and then they seal the top. And then as soon as you take that top off, the pressure lowers. You release the pressure, and a lot of it's going to escape. There is actually a formula that allows us to calculate the concentration of dissolved gas as a function of pressure. K is simply a constant, and so you have to be given that, as you have to be given most constants. This is called Henry's law. So you can see again mathematically, if you visualize math behavior better mathematically, which I tend to prefer that as pressure goes up, right, the concentration goes up, or if pressure goes down, concentration must go down. Pretty easy formula to use. Here's a sample problem. And let me write out the formula here. So the concentration of dissolved gas is Henry's constant, which is different for each system, times the pressure. All right, so I see. So this is, it's switched from concentration. So sometimes Henry's law is in terms of concentration, which is a C. Sometimes it's in terms of solubility, which is an S. Same thing, okay? Sorry about that. All right, so solubility or concentration of dissolved gas. Henry's constant must be given to you, which it was. Watch your units, though, okay? Make sure that everything matches. And pressure, now since Henry's constant was given to us with atmospheres, pressure must be in atmospheres. So this problem was nice. It gave everything in the correct units. And then you get solubility or concentration in moles per liter, which is molarity. And there it is. Pretty easy, huh?